This is Sean Murphy with Bicycle. Today, I'm going to go over the current input data logger, the DL4000, 40C, 20C, and 10C. The DL4000 is for capturing analog inputs that are scaled in current milliamps. The overall range for the DL4000 current input logger is 0 to 22 milliamps. But effectively, with just about every application, you're going to be scaling the data logger between 4 to 20 milliamps. And that's pretty much the industry standard for analog output transmitters. First is the overview of what the DL4000 data logger looks like. It's a small data logger. It has 4 pins up in the top where the analog inputs come from your transmitters. There's screw terminals that are in these little adapter pieces that remove from the top of the data logger. And the data logger features 2 different connections. One is a D9 connector for connecting to external digi devices. It's RS232. And underneath it, there's the VNet connector. This is for the specific to the VNet module. That's a single port network adapter. The DL4000 data loggers, like all the other data loggers in the DL series, they primarily communicate using RS232 serial. Serial port servers are required to be able to convert the serial communications over the network. So there's always another device, typically with a viewLinc integration. You're either using a VNet or you're going to be using a digi. And there's details in other videos and presentations on those devices. I can be focusing primarily on the actual data logger itself, how it's terminated, and how to wire devices to it. The data logger itself is configured to have non-isolated analog inputs. In other words, all these inputs, the common terminals, are the same inside of it, like there's a large bus bar across those terminals. You can see it labeled on the data logger as being 1C, 2C, 3C, 4C. The 4 to 20 milliamp signal goes into between 1 and C. So that's where you connect the first channel, and 2 and C go to the second channel, and so on through channel 4. The screw terminal block, there's 4 of these that come with the data logger. These are removable. There's a little tab that you pull to pull these out, and there's screw terminals underneath it. So you'll have 2 leads coming in from the to the data logger from the transmitter. One will be the channel input, and the other be the common. And these sockets are removable. They're slightly different when they're configured in a CAB 100, where they're all the 4 pins are all together as one socket. And I'll get into that in a few minutes. CAB 100B is an analog input panel. It supports various transmitters inside the panel, but it also supports data loggers inside it. So there's various configurations. You can do up to 32 4 to 20 milliamp channels, loop powered, and you can also do external power. The device is also capable of differential pressure transmitters, and those come factory pre-configured, and there's really no need to do any wiring when you get a panel that has transmitters already built into it. Then there's also the option for up to 16 Zener barriers, and those are specifically for our HMT 370 transmitter that's intrinsically safe. The data loggers themselves, they mount in brackets into the back panel of the CAB 100. And there's actually 2 different versions of the CAB 100. It's the CAB 100A and the CAB 100B. Typically, the CAB 100A really only supports 1 data logger, so that's more for differential pressure than it is for analog inputs. But as you can see, the data logger is mounted inside a DIN rail bracket. It's the same data logger as what I was showing you before. It's just in this bracketed assembly for mounting inside of a panel. When you're terminating to a data logger in the panel, you're typically doing your terminations to a terminal block that's independent of the data logger itself. So the standard configuration for CAB 100B with 4 to 20 milliamp inputs is going to be loop powered. So in other words, it's not just connecting just to the terminals on the data logger, it's actually connecting to the power source on the panel, providing 24 volts injection into the signaling loop. The panel can be reconfigured to support externally powered devices where the power is coming from the transmitter itself and it's not being injected by the panel. And this is the basic wiring diagram for all loop power transmitters. This is pretty much a generic wiring diagram for any analog input device that has non-isolated inputs. You have the DC power supply that's wired directly to the loop power transmitter. It connects to typically it's labeled as the positive terminal on the transmitter, and there'll be a negative terminal on the transmitter, and that goes to the inputs on the data logger. So essentially you have one power lead going out to the transmitter and 4 leads coming back if you have a 4-channel device. This is a detailed view of the CAB 100 loop power. So this is taking a look at that terminal block that's inside the CAB 100 panel. The first row is all the negative terminals. The top row is all the positive inputs. If you remember from the wiring diagram that I showed you earlier, the inputs are all the positives and the outputs are all the negatives. So when you go over to here, this is the positive and this is the negative for your wiring of each one of your transmitters. All the transmitters share a common positive. That might be counterintuitive to a lot of people's thinking that common is typically ground, but when you're supplying power to a loop, you're actually injecting the positive power into the transmitter from the panel and receiving on the negative terminal into the data logger, just like this drawing shows, where all the commons are all connected together on the data logger, and the loop power transmitter channel output goes to the input channel. And there's more details inside the CAB 100 manual that gets into the explanation of what this bus bar is on here. But essentially, these pins down here that you see, these go directly to a data logger. So this first one on the lower left-hand corner, these are all the inputs that go directly to the DL4000. So the white wire goes to channel 1, brown wire goes to channel 2, green wire goes to channel 3, yellow goes to 4, and the black wire goes to the common on the data logger. It only lands once on the data logger as being a common because, as I mentioned before, the common on the data logger is common for all 4 channels. So they're grouped in the terminal block. Depending on what you have for a panel, it may have more or less of these terminals. This block here supports 3 data loggers. You can see channel 1, channel 2, channel 3, channel 4 up at the top, and then right next to it will be 1, 2, 3, 4 for the second data logger and 1, 2, 3, 4 for the third data logger. So these blocks really connect multiple data loggers to a common block. And if you look at the little orange things that are underneath each one of those sockets for wires, that's a spring-loaded clamp. So if you press down on that little orange button underneath, it opens up the jaws on the clamp, and you put your wire in there, and you let go of it, and gives a good solid grip on your wires. The next thing that we're going to look at is the DL4000 Current Input Logger wired differently. And you'll see this with Indigo 520s or any kind of transmitter that provides a powered output. So in this case, the power for the 4 to 20 milliamp signal loop comes directly from the transmitter. The panel is not injecting any power into it to create that 4 to 20 milliamp loop. The wiring on here is rather easy to understand. The transmitter has a positive and the transmitter has a negative on every channel. When you actually configure this, you're basically taking all the negative terminals on all the transmitters that are connected to the same data logger, and you're tying them all together. So that's something to think about when you're wiring different transmitters from different places, they're all going to have their negative terminals converge. They'll have a virtual common ground across all of them. With externally powered transmitters, you typically are looking for a power supply for the transmitter itself, whether it be a humidity transmitter or whether it be another piece of equipment that requires power. Maybe it's a pressure sensor or something like that, where the device will actually power off at 24 volts. You can actually tap the CAV 100. There is a power block in the lower right-hand corner of the panel that gives you direct access to power. The terminals have a pattern to them. On the bottom strip, you can see where I had labeled power plus and power minus. That pattern repeats across that entire bar on the bottom. The bus bars that are above it, the red one, that connects all the positives together, and the blue connects all the negatives together. So essentially, this acts as a giant power block. You just bring your positive and negative power leads and connect right where I'm indicating on there, or any one of the pairs that are along that lower rail. You'll notice up above where it says 1, 2, 3, and 4, those are the power connectors that actually go to the loop powered injectors for each one of the data loggers that are in there, the power 4 to 20 milliamp. So those would not actually be installed if you were using this for external power, because you wouldn't be wiring the transmitter 4 to 20 milliamp. And I'll get into that in a few minutes. One thing, if you're going to be tapping this power supply, be aware that the power supply itself is not unlimited power. This is a 60-watt power supply, and it's also powering either 1 or 2 Digi TS4s, which are serial port servers. You'll have one TS4 if you're between 1 to 4 data loggers inside the panel, and you'll have 2 of them if you have 5 to 8 data loggers inside the panel. So to do a little bit of math to figure out how much power you have for each one of these channels on the device, on the entire panel, you take 60 watts, subtract out the 6 watts for the single port Digi, and give yourself an extra 20%. You don't want to overutilize a power supply, so you give yourself an extra budget of 20%. Essentially, by taking 80% of the full power output capability, you end up with 43 watts. Or when you divide it over 16 channels, you have 2.6 watts. And when you go to 32 channels, you're really stretching the power budget. You only have about 1.8 watts per channel. So it's limited what you can power from the panel. Typically, if you're taking a particle counter or a device or transmitter that requires significant power, a good example would be our Indigo 520 that has a lot of electronics to it, draws a lot of power. That requires too much power to really be powered off of this panel. So it's available power. This is maybe good if you're trying to power maybe a Magna Helix or some other kind of pressure transmitter or something that's very low power. Otherwise, you're going to be looking to power that on either AC or use a larger size power block. Now, the termination for externally powered devices is very different from the loop power. If you notice, the configuration of the terminal blocks are completely different. This is because you actually have to modify the panel. You have to follow the instructions inside the manual that tell you how to unconnect, reconnect, and move the bus bars on the input block. And the reason for doing this is because with the loop powered, you're actually sending power to the transmitter and then taking the power back from the transmitter and putting it into the data logger. So essentially, we're injecting power with the loop powered version. This version doesn't have the power block connected to it at all. This is purely a passive input. And the way the terminals work on here is you can see the same connector that was in the previous picture for the loop powered. is now in the upper layer of the terminal block. And all this is doing is allowing you a place to connect into the terminals that are on there. So you'll see the where it says channel 1 minus, all those channels along the back there, they're all wired together, and that's the common. So every channel that you have coming in here is going to have a positive and a negative, and all the negatives need to go to the negative terminal on the data logger, and that's what that little black wire is, and that's what all the negatives go to. Okay, so this is the view of the terminal block when it's configured for external power. Now, you'll notice that the layout here is very different, and that's because you have to modify the terminal blocks to connect externally powered devices. Because by default, the panel ships with a 4 to 20 milliamp loop injection, so you have to modify the bus bars and the connectors on here, so it's no longer injecting power. The setup here is actually quite simple. You're connecting into the data logger itself, and all this does is give you a better place to connect the terminals from your transmitter than what I had showed over here with the data logger itself, where you have these, direct pins. You can actually take the transmitter and wire it directly to the channel 1 and the C and the channel 2 and C on the data logger itself, and not even use the terminal block. So this is an option for nice terminals on here, is to actually use the terminal blocks, but you can always go directly to the data logger itself. And also in a situation where you want to add just an extra data logger inside the panel, as long as you have a slot open on the digi to be able to connect this data logger in, we do sell the brackets and the connectors in here for you to add an extra data logger inside the panel. This picture over here shows you how you would take a transmitter that has powered outputs and land it onto the terminal block. It's the same type of layout as you have with the loop powers configuration, where you have a block of 5 pins that are associated with the each individual data logger. So you have logger 1 and logger 2, and then there's a possibility for logger 3 over here if there was another socket in this particular panel. You'll also see data logger 1 and data logger 2 have connectors up above it. The first layer, where it says channel 1 positive, that entire row is dedicated to all the positive terminals coming from the transmitters. The row behind it up top, that's for landing all the negative leads coming from the transmitters. And they're always paired just like they are with the loop powered. Channel 1 is the upper and the lower in the first section. And you can also see what pin it's aligning with. For example, under this logger number 1, you see the white wire. That's actually the wire that goes to channel 1 on that data logger. And if you take a look at the data logger itself, you'll notice that the first 4 pins line up directly with the inputs on the logger. Now that we've gone through and done all the wiring to the data logger, the next thing is to go into viewLinc to configure it. I'm not going to cover the part where you set up the digi port server. There's other information available to show you how to do that. But at this point, we have now discovered the data logger inside viewLinc, and we're adding the data logger configuration. So the first thing you're going to want to do is open up the data logger in Sites Manager under Hosts and Devices, and navigate down to open up the device. And you're going to want to edit the device properties. One is to give the data logger a name. This is so you can have a name for the device that shows up under the list of devices in viewLinc. The next one is the sample interval. By default, these should ship with a 5-minute sample interval. You can go down to a 1-minute sample interval and still get a 10-year battery life out of it. Don't go much below, don't go below 1 minute unless you're going to change this temporarily to maybe do a calibration for on the device. I would only do that on a temporary basis because you're going to limit the life expectancy of the data logger itself. So typically it's a 1 minute sample interval, and the then you have channels 1, 2, 3, and 4, and with the channels, you're going to want to make sure that each one of those channels is enabled. And then you open up each one of the channels. So that was for the configuration of the data logger. If you now navigate down to each one of those channels, each one of those channels will be given the default name of current, and it'll be scaled in milliamps. Now, you don't want to link this to any locations inside of viewLinc until you go in here and actually scale the logger and give it the correct engineering units. So you're going to want to give the channel a name and the data logger. This just makes it easier for you to manage the location when you're dragging and dropping these into locations from the device manager. There's a couple of settings that you need on here. One is going to be the 0 milliamp value, and the second is going to be the span milliamp value. Now, every transmitter that's out there that's 4 to 20 milliamp, they're going to come with a typically a label underneath it that says 4 to 20 milliamp, and then it'll give two other numbers. It'll say, and those two numbers are going to be your 0 and your span value. For example, it could be, in this case here, a differential pressure transmitter that scales between 0.25 negative inches of water column to 0.25 inches of water column. And so that's what this is scaled as being, is from the 0 value of negative 0.25 to 0.25, which is the span value. And also I'm going to enter in the units. And under this configuration, I'm showing INWC for inches of water column. This would be any other type of measurement if you had it in Pascal, or this was in humidity or temperature, or if it's in temperature, you actually want to put in DEGC for degrees Celsius. So once you configure this, before you can actually get this to work properly, you need to make sure that you have those units, those engineering units, as units in viewLinc first. Otherwise, you're going to run into problems when you try and create locations for device units that don't exist inside of viewLinc. You have to configure that. And that's part of that's under preferences. So as long as you have the units existing inside of viewLinc system, you should have no problems with the labeling. And another note is this is showing scaled 4 to 20 milliamp. It has the capability of going from 0 to 22 milliamps. That's the full range. It's very rare to see a transmitter that's scaled 0 to 20 milliamps. Sometimes it's an alternative configuration. But I always recommend, even in the event that you have something that scales 0 to 20 milliamps by default, if you can reconfigure it, I would reconfigure it to 4 to 20 milliamps. And the reasoning for it is that when you scale 4 to 20 milliamp for your analog outputs, it gives you an advantage over scaling it from the 0 milliamps to 20 milliamps. And that advantage is that you have a live ground, a live 0. So the low end of the transmitter scale is 4 milliamps. So anything that's below 4 milliamps is off scale negative. And some transmitters may have some overranging to them, but most of them with 4 to 20 milliamp do not. You typically only see overranging with voltage devices. So with the 4 to 20 milliamp, if you're getting a value that's 3.5 milliamps, it may actually correspond to an error code on the transmitter. If it's reading 0 milliamps, it means that you have no power in your 4 to 20 milliamp loop. So basically, any reading that comes in below 4 milliamps is an indication of a fault in the transmitter itself. So, which is actually very different from a voltage device. Voltage, it always scales from 0 to 5 volts, 1 volt, 10 volts. You don't know when you have a value of 0 whether it's a dead transmitter or it's an actual value at the bottom end of the scale. So that's my 2 cents when it comes to uh, 4 to 20 milliamp signaling, being superior to voltage. The fact that you have this live 0.